In the last video, we had gotten as far as coming up with the existence of potential energy functions. And the beauty of these is that they depend only on the type of force and the relative positions of the objects that are interacting via that conservative force. So now we're going to see where this becomes super useful. So we're going to take our first version of the Work-Energy Theorem, also called the Work-Kinetic Energy Theorem, which says that the net work done on something is equal to the change in the kinetic energy. Now, we can break up the net work into the work that is done by non-conservative forces plus the work that is done by conservative forces. You're either one or the other, so that includes them all. So let's subtract the work done by conservative forces from both sides. So you get the work done by non-conservative forces will be equal to change in kinetic energy minus the work done by conservative forces. But by how we constructed potential energy, we said that any potential energy function always had to satisfy the condition that the change in potential energy would be equal to the negative of the work done by the conservative forces. Now you know why the minus sign. So we get that this is the change in the kinetic plus the change in the potential energy. Or if you want to get all fancy, you say that the work done by non-conservative forces is equal to the change in the mechanical energy, which is the sum of the kinetic and the potential. Now, it turns out that this fact that the potential energy only depends on the coordinates can be very useful. So when we're looking at using energy conservation to solve a problem, first off, our biggest hope is that non-conservative forces such as friction are not present. If they are, we have a mechanism for coping with that, and we'll get there. We will want to cleverly choose our coordinate system. For instance, if gravity is involved, usually you want to put y equals 0 at the bottom of the problem, just to make all the energies positive, unless there's some really good reason otherwise, like the problem gives a very natural choice of 0. They say, how high above the ledge, or something like that. And then what we're going to do is just add up the forms of energy we have before and after, equate, and solve, substitute, and check units. So we'll start with going back to our friend throwing a rock off a cliff. So let's say that we have a 5-meter high cliff, like so. Here you are, about to throw a rock off the cliff, and you throw it horizontally at 10 meters per second. Now, we've seen earlier that the rock is going to follow some sort of parabolic trajectory. And what we want to know is just before impact, what was the final speed of the rock? Notice I'm not asking what the velocity is, just the final speed. But sometimes that's all we need to know. So we can go and say, well, are there any non-conservative forces? Well, we always neglect air resistance. So since we're neglecting air resistance here, then we don't have to worry about drag. And there is no friction. And since we said just before impact, we don't have to worry about any work the normal force or friction from the ground might do on our rock. Okay, so for a problem like this, we can look and say, all right, the work done by non-conservative forces is equal to the change in kinetic plus the change in potential energy, but there are no non-conservative forces. So what does this mean for us here? Well, what this means for us here is that this is going to be equal to K final minus K initial plus U final minus U initial. And so we can rearrange to get K final plus U final equals K initial plus U initial. In other words, the total mechanical energy at the end will equal the total mechanical energy at the beginning. But it'll be more useful for us to itemize it out. In fact, when I look at problems like this, I actually like to take a page from our friends who do accounting and actually make a double entry bookkeeping type arrangement here. So all I'll do is I'll make a table of all the forms of energy I can think of. So, and you'll notice that we will write expressions for what we have at the beginning and at the end. Well, for this problem, I can only think of that there's kinetic energy and gravitational potential energy. Now, there may be more than one form of potential energy in a problem, so it's good to get in the habit of itemizing them out. But here we only have gravitational potential energy. So we can go and write our expressions here. This would be 1/2 mv final squared. This here would be 1/2 mv initial squared. This would be mgy final. This would be mgy initial. And here's where it's talking about that since you're free to choose where y equals 0 is with gravitational potential energy, let's say that y final at the bottom of the problem here is 0. This will make y initial equal to 5 meters, but at least it gets rid of one of my potential energy expressions. So by setting y final to be 0 at the bottom, that makes the potential energy 0 at the bottom. Then what you do is you just add up the columns. Actually, let me move this over. There we go. So we can go ahead and add up the columns, and we will have, on the final side, we'll have 1/2 mv final squared, and that'll have to be equal to the column on the right-hand side, 1/2 mv initial squared plus mgy initial. And once again, it's a really good thing that the m's cancel out because I never said what the mass of the rock was. Now we can go ahead and solve for v final. So first thing to do would be multiply through by 2. So I'll have v final squared equals v initial squared plus 2g y initial. And then finally we can say v final is the square root of v initial squared plus 2g y initial. All right, so let's go ahead and put in our values. So we'll have the square root of 10 meters per second squared plus 2 times 9.8 newtons per kilogram times 5 meters. And it will once again be useful to write newtons per kilogram as meters per second squared, and all the units check out. We will be left with 14.1 meters per second. All right. So now what I want to do here is I want you to go back and think about this problem some more. And what I want you to do is I want you to think about, what if instead of throwing the rock horizontally, I threw it at a 45-degree angle above the horizontal, again at 10 meters per second. So that's the first situation. And then for the second situation I want you to think about, what if I threw it again at v initial 10 meters per second at 45 degrees below the horizontal. So in each case, I want you to predict whether the final answer will be higher, lower, or the same as before. So go ahead and pause the video for a bit, think it through, and then when you're done, go ahead and unpause and get back with me. Okay, so you're probably going to be a little annoyed about it, but let's just think about what happens here. So I can go ahead and write down my initial kinetic energy. It's still this exact same value, 1/2 mv initial squared. Kinetic energy only is associated with how the mass of the object and how fast it's moving. It doesn't care which way the object is moving. So it turns out that in all three cases, the rock is going to hit the ground going at 14.1 meters per second. Now, the trajectories that the rocks took will be very different. This one will probably look something like this. This one's probably going to look something like that. Very different trajectories. And you can even convince yourself very different times of flight. If I throw the rock downward, it will get to the ground sooner. And if I throw it in a generally upward direction, it's going to take longer before it hits. And you'll notice too, we can't say where it hits. But we can say that when it hits, it will be going at 14.1 meters per second. This is an important trade-off in doing energy analysis. It is really super useful for the problems that it lends itself to. But the caveat here is that you always throw away information regarding the trajectory, so the actual path followed, and time evolution information. In other words, where was the rock at some specific time? So throwing away the trajectory information, that kind of makes some sense. Remember, we said that for a potential energy function, in order to have one, the force has to be conservative. So that means that between 2 points, no matter what path you take between the points, the work done by that force would be the same. So the change in the potential energy would be the same. So in this particular case, it's even a little worse than that because the potential energy only depends on the height. So we can't even guarantee that it's going to close back at a particular point, just somewhere at y equals 0. That's all we know. The other thing that we throw away completely is absolutely nowhere in here does time show up for anything. So if we need to know the direction it was going, or we need to know where it was at a specific time, we'll have to go back to doing Newton's laws of motion and solving the dynamic situation and probably tie that in with some kinematics. So, but if we don't need that, and a lot of times we don't need that, then energy analysis will let you rip through a problem like a hot chainsaw through butter. And keep in mind, this isn't as awful as it may sound. A lot of times you know the trajectory, right? Say you're looking at a roller coaster, you know that the roller coaster is going to stay on the track, so you know the trajectory. So in a situation like that, the fancy physics term is we say that you're exploiting the constraint. You know that the object is constrained to be on the roller coaster track, so you know the trajectory. So since you know the trajectory, you don't really feel a burning need to solve for it already. So a lot of times we'll have those kind of constraints, or, say like an object is, a skier is going down a hill. The skier is on the hill. So again, you know the trajectory. And sometimes you can use some of the information you get, loop it back into kinematics. So there are tricks you can do, but keep in mind the main limitation is that you're throwing away trajectory and time evolution information. And so if you need those, you're going to have to be more clever. That may or may not involve solving Newton's laws of motion, but you'll at least have to be more clever. All right. So now let's do another problem. And this time we will have a problem involving friction. So let's say that we have a box going down a ramp. Let's say the angle that the ramp makes is our old friend 37 degrees. Let's say the box starts at rest and we just barely nudge it. To just enough to break static friction, but it isn't really going to affect anything. Let's say that the box displaces down a total of 5 meters. So we'd like to know when it gets down here, how fast is it going? In this case, we already know the direction. The direction is going to be parallel to the ramp pointing down. So we don't have to do any fancy work there. So if we get the speed, we can completely describe the velocity. Since we are having friction happen here, we'll go ahead and say that the coefficient of kinetic friction here, is 0.25. All right, so let's follow through our work-energy theorem, second form work-energy theorem again here. Work done by non-conservative forces is equal to the change in kinetic plus the change in potential energy. And I just want to follow this through to see where this is going. So we can say work done by non-conservative forces is K final minus K initial plus U final minus U initial. And we can rearrange. Rearranging, we will get K final plus U final equals K initial plus U initial plus work done by non-conservative forces. So if we want to do this by a table, we would be inserting our variance, if you will, on the initial side. I'll show how that works in a moment. Now, unfortunately, in this case, you can't completely escape Newton's laws of motion. The only way to calculate the work done by non-conservative forces is to calculate the force and times it by the displacement times by the cosine of the angle between the force and the displacement. Unfortunately, there's just no sugarcoating around that. So let's go ahead and start by drawing a free body diagram for our mass. So we'll have a normal force and a force of kinetic friction and a force of gravity like so. And again, following the second law of inclined planes, this angle here is that angle there. So we can say that this is FGY and FGX as we go ahead and follow the first rule of inclined planes and tilt our coordinate system. All right. Now here, though, instead of us having to go to the effort of figuring out all the accelerations and all that, our only game in town is to try to figure out work done by non-conservative forces. So first off, with gravity, we don't care. It's conservative. So since gravity is conservative, that's already taken care of by the potential energy function. So for that, we will have to figure out how high y initial is. So let's just go take care of that right now. So we'll set y final to be 0 at the bottom of the problem. So then this would make y initial here equal to our displacement d times the sine of theta, 37 degrees. All right, so now that we got that, we have our expression for y initial. We're good to go there. So gravity's taken care of because it's conservative force, or at least taken care of for the moment. So now let's go ahead and come up with the expressions for the non-conservative forces in the problem. We'll start with the work done by the normal force. Here we are doing super good because the normal force and the displacement make a right angle. So since they make a right angle, the work done by the normal force is 0. We don't have to worry about it. Okay. So now that leaves us with figuring out the work done by kinetic friction. So we'll say W sub k here. All right, so here, force of kinetic friction points against the motion. There's our displacement. So the angle here, phi, is 180 degrees. So our first step will be to say that the work done by kinetic friction will be equal to the force of kinetic friction times the displacement times cosine phi. And cosine of 180 degrees is -1. So we can write that as minus fkd. All right, but looking ahead, we have to more sensibly express the force of kinetic friction. We were given a coefficient of kinetic friction, so we know that this is going to be equal to minus mu k times the normal force. So here is unfortunately where we are going to have to do a little bit of dynamics, but not as much as we had to before. We still need to find what the normal force is equal to. So we're still going to have to write something like F net equals ma. But here, the normal force is acting purely in the y direction, so we don't have to look at the x at all. So in the y direction, the normal force is acting up. And then we only have this bit of gravity here, FGY, acting down. So it'll be FG, and that'll be the cosine, because this is the adjacent, of our angle, the ramp, theta. That's different than this angle phi between the force and the displacement. That was 180. This is going to be 37 for the ramp. And then this equals ma sub y, but a sub y is 0, so that drops out. So the normal force is equal to Fg cosine theta, or mg cos theta. So armed with that, we can go ahead and put in for the work done by kinetic friction. Now we can say it's minus mu k mg cos theta. So now we've got our expression for the work done by kinetic friction, and that frankly is the hardest part of the problem. All right, so when we add up our forms of energy here now, again, you're going to make a table, initial, so again, we write down all the forms of energy we can think of. So now we're going to have kinetic, gravitational potential, and now we need to be just a little more careful here. We're also going to have to throw in the work done by non-conservative forces. We're basically treating this the same way an accountant would treat a variance. That's where when the books don't balance, say somebody five-finger discounted something from the till or something, they have to note the variance and they have to put it on just one side of their ledger. So we're going to do the same thing. So whenever we put in this variance for work done by non-conservative forces, first thing I do is just put a big huge box right there on the final side so I don't feel like writing anything there. And so now we can go ahead and put in our expressions. So our expression for our final kinetic energy will be 1/2 mv final squared. Our initial kinetic energy, well, we nudged it from rest. Starting from rest would mean it's 0. Our final kinetic energy, final potential energy is 0 because we set y final to be 0 over here. So for the initial, this will be mg y initial, and I'm just going to immediately substitute in that that'll be mg, and we worked out that our y initial is d sine theta. And now we have to tuck in our variance, and we always, with the non-conservative work, the only non-conservative work we have in this case was that from friction right here. So you just go ahead and put that line in right here, minus mu k mg d cosine theta. All right, same deal. We go ahead and add the columns up. So we have 1/2 mv final squared equals mg d sine theta minus mu k mg d cosine theta. Once again, since I didn't give you the mass of the box, it's a really good thing that it canceled. All right, so let's just do a bit of algebra on this to try to clean this up a bit. First thing we'll note is before we even get around to times by 2 and taking roots and stuff, there's a g and a d in both of these terms, so let's pull it out. G, d, so we'll have sine theta minus mu k cosine theta. All right, now let's times through by 2 and take the square root of both sides. Doing that, we will get v final equals the square root of 2 gd sine theta minus mu k cos theta. So now we can put in our values. So this will give us 2 times 9.8 newtons per kilogram. And once again here, we're going to want to recast that as meters per second squared. Times our displacement, which was 5 meters, sine 37 minus 0.25 cos 37. Okay, put that all through your calculator. You get 6.26 meters per second. All right, not going to lie here. This problem was definitely more of a chore than when we were just throwing the rock. We still had to do some Newton's second law to come up with an expression for the normal force so we could properly express the force of kinetic friction, so we could come up with the work done by kinetic friction. And unfortunately, that's just always going to happen whenever you have to find the work done by dissipative forces. You're probably going to have to do Newton's second law or something. You're going to have to do more. You're going to have to expend more effort to figure out in a suitable expression. But compare that to when we were doing this purely by forces and kinematics. When we did this by forces and kinematics, we also had to go and take a look at the x equation of motion and come up with an expression for the acceleration, and then we had to use gang of 4 to use the acceleration to get the final speed. Here we didn't have to do any of that. So even though we still had to do a little bit of a slug to figure out the work done by kinetic friction, wasn't the end of the world. It still made the problem substantially easier to solve than we would have had before. All right, so that's going to raise a natural question, which is, where did that energy go, right? When I go ahead and I'm inserting a variance here, that seems a little cheeky, right? And turns out we can indeed account for where that's going. Remember our model of friction. So when we have the box sliding down the ramp like so, if you remember in our model of friction, we said that the surfaces aren't perfectly smooth. So let's say this is the surface, and let's say this is the surface of the box. Now what's going to happen is that sometimes these jaggies are going to overlap right here. Okay, so I will highlight that out right there. And when we get these jaggies bumping up against each other, what's going to happen is that initially they're doing something like this, being just right up against each other like so. And then as this one's moving by like this, they're going to bend. So later, this one's going to be bent over, say, like that a bit. And this one's going to be bent over like this a bit as they're moving by each other. And then what will happen is at a molecular level, these things are just going to spring back and forth. So we call this thermal energy. And what's happening here is that atoms and molecules are having their kinetic energy changed. And also the potential energy associated with their bonds. So this micro just means microscopic. So when we say that energy, quote unquote, isn't conserved, we know that deep in our heart of hearts it really is. And so it would be more correct for us to balance out the books by saying the work done by non-conservative forces would be equal to the change in kinetic plus the change in potential plus the change in the thermal energy of the system. And so then we know where it's going. So long story short, when a physicist says energy isn't conserved, they know deep in their heart of hearts it is. What they're really saying is it's going to be really, really hard to calculate this because I would have to sit and think about individual atoms and molecules. So I'm just going to say, yeah, that energy went over there and leave it at that. All right, one other thing, I have two other little things to throw in here, and then in the next video we'll look at elastic collisions. So a term that people often confuse with energy is power, and they're not the same thing. Power is defined, it's capital P, it's defined to be the work done on something over the time it took to deliver that work. So, pardon me here. Yeah. Or we can say it's just the change in the mechanical energy system over the time. You can show, but it's beyond the scope of this course, that the power delivered by a force will be equal to the force times the velocity of the object that you're pushing, that you're pushing. So the units of power are annoyingly a capital W for watt, after James Watt, steam engine dude. And a watt is a joule per second. So this is work, this is a watt, not the same thing. In a book, this would be written in italics, and this would be written upright. When you're writing by hand, unfortunately, it doesn't really show up. So this is the rate at which energy is being transferred. So this does lead to an interesting question. When you get your bill from the electric utility, you're almost always billed in, unless you're in Australia, in kilowatt hours. So I want you to ask yourself, is this a unit of power, a unit of energy, something else? Pause that and get back with me. All right, it turns out it's a unit of energy. Remember, the kilo prefix literally means 1,000. So 1,000 watts times hours. So we've now said that a watt is a joule per second. We're still timesing by hours here. So to get the units all compatible, we have to remember that 1 hour has 3,600 seconds. So then hours cancel, seconds cancel, and sure enough, we're left with joules. 3,600 times another 1,000. Turns out that a kilowatt hour is 3.6 million joules, or megajoules. Now, notice I said this is usually how you're billed for electricity unless you're in Australia. My understanding, unless things have changed very recently, is that for pretty much everything to do with energy, in Australia, they use joules. I have actually seen cans of Diet Coke that were labeled low joule cola instead of low calorie cola, for instance. But for most of the rest of the world, mostly for historic reasons having to do with how electric meters were designed, we get billed in kilowatt hours, and they're just units of 3.6 million joules. So if you want to amaze your friends and confound your enemies, you can take your electric bill, times it by 3.6 and quote it as megajoules, and that will sound certainly much more impressive. Okay. The one other little side topic I wanted to introduce here is efficiency. A lot of times in physics, there will be figures of merit, if you will. And so it's probably best just to think of an example here. As an example, let's say you're going up the stairs. Okay, maybe you're scaling a ziggurat, something like that. And let's say that over your ascent up this chunk of ziggurat here, your potential energy increased. And say if you're going up a flight of stairs, for a typical person, this is on the order of something like 1,800 joules. And again, if it's a flight of stairs, for a typical person, it turns out that you'll actually expend 7,200 joules-ish of food energy in the process. Now, where does this go? It turns out that there are two different kinds of limitations that you can have. There are fundamental limitations. As we get into thermodynamics, we'll see that it is impossible for certain kinds of processes to be totally efficient in converting one form of energy into useful work, such as raising yourself up a flight of stairs. And then there are also process limitations. Here, the process limitations are the bigger deal. If you consume 7,200 joules worth of food, that food needs to get broken down by the digestive system. That's going to take energy. I mean, you got to make peristalsis happen. That's going to take energy. Then as everything gets all broken up, goes into the bloodstream, you're going to have to form ATPs, and so that means you're going to have to run the Krebs cycle. Round and round the Krebs we go. And so you're going to be looping around the Krebs cycle to get your, to make the ATPs to go up the flight of stairs. At every step along the way, there are losses because they're mediating molecules that will take some of the energy away, etc., etc., etc. Now, general rule of thumb, where does that extra energy go? Thermal energy. And that's why you start sweating. All right, so we can define the efficiency, and we'll just use a lowercase e for efficiency. Almost any figure of merit like this gets defined as what you get over what you had to pay. So here, what did we get? We got 1,800 joules of useful work raising you up the flight of stairs. What'd you pay to do that? 7,200 joules of food energy. In this case, you literally paid to get that food to put it into your body. So anyway, that works out to be about 0.25, so 25%. Alrighty. So in the next video, we will take a look at elastic collisions. These are collisions where both momentum and energy are conserved. We'll catch you on the next slide.